So today is the first online meeting. So we are going to try this out. I've tried it once before, did not work out. I'm very sad, I know. So for a part of these notes, some of it's going to be already pre-filled in because I wasn't smart enough to print off more than one copy, or maybe I just thought I was better than what I really am. So I'm so sorry some of it is pre-filled out already. That is completely my fault. So I apologize. But, so I'm doing this again. You're hearing it for the first time. Remember that we are having quizzes to make sure that you're keeping up with the information. So please just monitor Canvas and your email to watch out for that, just because I don't want anyone falling behind. And this is more or less just to make sure that you have some, I don't know what to call it. You have something pushing you to do it. But anyways, I digress. So diving into the notes, we've got section 5.3, the second derivative. You'll notice this is very, very similar to the first derivative test. We're going to be running the second derivative test in here to describe concavity and inflection points. You'll see soon what the heck that means, but first, some notations. So the objectives we have: use the second derivative to determine concavity and inflection points. Again, we'll talk more about that here in a few pages. And then we've got one application, the point of diminishing returns, which is really gonna hone in and emphasize an idea that I want you all to really understand. All right, so notations. So the second derivative of a function f is notated f double prime of x. And it is simply the derivative of f prime of x. So which we now call the first derivative. So as you can see further down here, we've got first derivative notations, second derivative notation, third, fourth, and so on and so forth, right? So basically after the fourth, it's just fifth, sixth, seventh. Yeah, I think you get the picture. We kind of stop with the asterisks after the third. Sometimes it will be used for the fourth, but not a whole lot. Again, so here's the notation just for you to get familiar with, so that if it pops up, you know what the heck is getting asked of you. Let me move these papers out of the way. So then here we've got more notation where this is like take the derivative of, take the second derivative of, take the third derivative of, the fourth derivative of this, so on and so forth, right? So here's an example. We're going to find the second derivative of this function, right? So like it was stated above, all we have to do is take the first derivative. So f of x equaling x cubed minus 8x squared plus 3x minus 4 then becomes 3x squared minus 16x plus 3. So to get the second derivative, we just take the derivative of this derivative. It's that easy. Hopefully you agree it's that easy. I don't know, we'll see. So then y double prime, or the second derivative, is equal to 6x minus 16. Because again, this is just the derivative of the first derivative. Hopefully you have your notes with you and you're writing them down as we go. If you have any questions, please just kind of jot them down on your paper and then shoot me an email later, and I'm happy to clarify anything that's confusing you. Okay, so now we've got page 2, more examples. Okay. So we're going to find the third and fourth derivative for x to the 6th power. So how do you suppose we're going to do this? All right, yeah. We are going to take the first derivative, to get y prime equals 6x to the fifth. Remember power rule, bring the power down, take off 1. Then to get the second derivative, we take the derivative of this. So we've got 30x to the fourth. So to get the third, what do you think we do? Yep, same thing. Power rule, x to the fourth. So remember the 30 is a coefficient, so it just hangs out. So we've got 30 times 4x cubed equals 120x cubed. Okay, then y to the fourth. The 120 is now the coefficient, so remember it's just chilling, it's just hanging out. Power rule, x cubed, so 3x squared. So we get 360x to the first, right? I wrote first, but remember, you don't have to write x to the first power. It's implied. And then I just kept going for fun. Okay, so then the fifth would just be, the fifth derivative is just 360. So then the sixth derivative, if we kept going, would just be 0. Because remember, what's the derivative of just a number? 0. Perfect. Good, good, good. Again, here's my email right here. If you need to email me any questions, again, I'm super happy to answer any questions that you've got. So it's ld1168@txstate.edu. So one thing to notice about here is that what's the power of this polynomial? Or not power. Well, yeah, power or degree. 6. Perfect. So it's a degree 6, and notice we could only take 6 derivatives, right? So you can't really take any more derivatives than powers that you have. I mean, I guess technically if you wanted to get into the nitty-gritty, yes, the derivative of 0 is a number, so it's 0, so on and so forth. But you can't really get any number but 0 after the 6th power. So that's one thing to note. Whatever your degree is, that's how many derivatives of that function you can actually take, at least for a polynomial. Okay, so now we're going to talk about what the heck concavity is. So we've got concave up and then concave down. So a function is concave upward on an interval a to b if the graph of the function lies above its tangent line at each point a to b. So, what do you think the definition of concave down is? Yep, same thing, but just below. So on an interval a to b, if the graph of the function lies below its tangent line at each point of a to b, then we've got concave down. Okay, so what do I mean by that? Well, over here I have a little picture for you. So I just drew this function, this right here, this kind of, I don't know, golden. I've got concave up right here because notice if we draw like tiny little individual tangent lines, the tangent lines would be, here we've got that it is